Hello everyone, I am Nur Najakarina binti Muhammad and 07267 as a video editor. In this video, we will learn about Chapter 4, Capacitance and Dielectrics. There is 5 subtopics: 4.1, Definitions of Capacitance, 4.2, Calculating Capacitance, 4.3, Combinations of Capacitor, 4.4, Energy Stored in Capacitor, 4.5, Capacitor with Dielectric.
4.1 Definition of capacitance. A capacitor is a device that stores electrical charge and electric potential energy in a form of electrostatic field. This stored energy can be released in a controlled manner when needed. A capacitor typically consists of two or more conductive plates or electrodes that carry equal and opposite charges, most often written as positive Q and negative Q. These plates are separated by a non-conductive material called dielectric, which prevent the flow of current between the plates. When a capacitor is charged, the quantity of charge Q stored on is directly proportional to the potential difference V between the plates, where C is measured in farads F, Q is measured in coulombs C, and V is measured in volts V. Definition of capacitance. Capacitance is a measure of capacitor's ability to store charge. It is defined as the ratio of the magnitude of the charge on either conductor to the magnitude of the potential difference between the conductors. The unit of capacitance is in farad, where 1 farad is equal to 1 coulomb per volt. The capacitance of the capacitor depends on factors such as the size, the shape, and the separation of the conductors. Once again, the formula where it defines the definition is C capacitance is equal to Q charge over delta V potential difference. And the example of devices that uses the concept of capacitance are as follows: radio receivers, power supply filters, and electronic flash. 4.2 Calculating capacitance. There are several ways to calculate capacitance, depends on the type of capacitor. We have parallel plate capacitor, cylindrical capacitor, and spherical capacitor. The formula used are varies depending on the type of capacitors. For example, for the parallel plate capacitor, the capacitance is proportional to the plate area and inversely proportional to the plate separation, where electric field is uniform between plates and zero elsewhere. Whereas for the cylindrical capacitor, electric field between concentric cylinders are calculated using the formula as shown. As I mentioned before, different types of capacitor uses different type of formula when we are calculating the electric field as well as the potential difference together with the capacitance. So these are as follows for the spherical capacitor.
Hi everyone, my name is Niljaen. My number metric is S72130. We'll be explaining the subtopic 4.3. My subtopic with a series circuit. In a series circuit, all components are connected end to end to form a single path for current flow. So the total capacitance is less than any one of the series capacitor individual capacitance. The total resistance in a series circuit is equal to the sum of the individual resistors, and the total voltage drops is equal to the sum of the individual voltage drops across those resistors. So if two or more capacitors are connected in a series, so the overall effect is that of a single equivalent capacitor having the sum total of the plate spacing of the individual capacitor. Now I'm going to explain the formula that will be used to solve the question in series circuits. Firstly, C1 and C2 is equivalent to C total. In order to find voltage, we have to add V1, V2, V3 together. Then we can apply the V1 equals to Q divided by C1, V2 equals to Q divided by C2. Then after that, just add up. Then the total is equal to 1 over C1 plus 1 over C2 plus 1 over Cn. If the circuit contains only two capacitors, the product over the sum formula is in parallel circuit, the total capacitance is the sum of the individual capacitor capacitance. So the overall effect is that of a single equivalent capacitor have the sum total of the plate areas of the individual capacitor. The total charge is the sum of the change on each capacitor. So we can apply the formula of Qt equals to Q1 plus Q2 plus Q3. This is the formula will be used in a parallel circuit. From the equation, C equals to Q divided by V. So it follows that Q equals to CV. And if the charge is written in this form, and it will substitute into the above equation, and this equation result in C total multiplied by V equals to C1 multiplied by V plus C2 multiplied by V plus C3 multiplied by V. So after that, we have to divide that V in the equation to get the C total. So 4x4 is about work to charge on capacitor. In charging, total amount of work required to charge the capacitor from Q equals to 0 to a final charge Q equals to big Q. So the formula is W equals to integrate Q divided by C dQ equals to Q squared divided by 2C. In an isolated system with no non-conservative forces, the total mechanical energy must be conserved. The amount of external work to transfer dq amount of charge across the potential difference is dW equals to potential difference dq equals to Q divided by C dq. So now I will continue my subtopic 4.4 with the potential energy stored in capacitor. Capacitor store energy forms electric potential energy. So the work to charge capacitor is equal to the change in potential energy. UF minus UI equals to W external. The potential energy stored in the capacitor, which is in SI unit joule. The formula is U equals to Q squared divided by 2C equals to 1 over 2Q. Potential difference equals to 1 over 2 times C times potential difference squared. Discharging a capacitor refers to the process of releasing the stored electrical energy in a capacitor. The capacitor will store energy in the form of an electric field between the two conductive plates separated by an insulating material, which is called as dielectric density in an electric field. So for a parallel plate capacitor, we know that V equals to ED and C equals to epsilon naught times A divided by D. U equals to 1 over 2 epsilon naught times A over D times ED squared. So the formula of U equals to 1 over 2 is epsilon naught A times D by E squared. So after that, we have to divide it by the volume. V equals to AD. So U is equals to 1 over 2 epsilon naught E squared. The energy per unit volume in a capacitor is in joule per meter cube. The density of the energy stored is UE equals to 1 over 2 epsilon naught E squared. And the SI unit is same as the energy per unit volume in a capacitor, which is joule per meter cube.
In a conductor, there are free moving electrons in it, so the electric field applied to it will be completely cancelled by the induced electric field produced inside the material. However, for dielectric, there are only a few free moving electrons, so the induced electric field inside the dielectric material will be smaller than the applied electric field. Hence, the resultant electric field will be smaller than the applied electric field. This causes the voltage between the capacitor plates to decrease, and the battery needs to pump more charges to the plates to keep the voltage between them same as the battery. For every material, they have different dielectric constant. If the dielectric constant is high, it means that the material can store more electrical energy. Then, for the definition of the dielectric strength is stated as in the slide, and it can be calculated by using the formula electric field max equals to maximum voltage divided by the distance between plates. We can calculate the capacitance of a capacitor that has a dielectric between it. Okay. Then there is also a formula C equals to epsilon A divided by D. Epsilon is the permeability of a material, and A is the area of the plates of a plate, and D is the distance between plate. And with this, we can find the capacitance of a capacitor using this formula. And then we can find the capacitance for the plates that have a dielectric between it. The experiment we choose for this chapter is an experiment of investigating electric field dynamics in a parallel plate capacitor. For the introduction of capacitors consist of two conductive plates which is separated by a dielectric material, and they are the fundamental components in electrical systems as they can store energy in the form of electric field and then releasing it as electrical energy when needed. And the objective of this experiment is to understand and determine the relationship between voltage, electric field strength, and plate separation in a parallel plate capacitor. The equipments or apparatus that we use in this experiment is a parallel plate capacitor, power supply, electric field meter, multimeters, and also the connecting wire. Next, for the procedure of this experiment, firstly, we have to connect the capacitor plates. The capacitor plates are connected to the power supply, and the voltage is regulated to investigate its effect on the electric field. Next, we will measure the electric field intensity between the capacitor plates by using a multimeter which is connected in a parallel circuit to the electric field meter circuit. And for the part 1 of this experiment, we will be changing the input voltage from 100 volts to 300 volts, and then we will be measuring the corresponding electric field intensity while keeping the plate distance constant. In this case, is 5 cm. This experiment can help to determine the relationship between voltage and electric field. For the part 2, we will be changing the distance between the capacitor plates, which is from 2 cm to 4 cm and 6 cm and so on until 14 cm, while maintaining a constant voltage to study the effect of plate separation on the electric field. For the theory part of this experiment, we use the E equals to V divided by T to find the electric field intensity of the capacitor. And in the formula, E stands for electric field intensity in kilowatt per meter, V is the voltage input in volts V, and D is the distance between the plates in meters. And for summary, this experiment utilized a parallel plate capacitor to measure how charges in voltage and plates separation affect the electric field strength. This relationship is crucial for understanding the behavior of capacitors in various electrical applications. Lastly, from this experiment that involves a parallel plate capacitor, we can gain valuable insights into the fundamental principles governing the behavior of capacitors. By systematically varying the voltage applied across the capacitor plates and the distance between them, we can observe how these factors influence the electric field intensity, strength, or intensity within the capacitor. And specifically, we can find that the electric field strength is directly proportional to the applied voltage and inversely proportional to the plate separation. And this has shown that the formula E equals to V over D has been proved in our experiment.
There are 6 references that we use to complete this video.